Medha is a first-year PhD student here at UTIG, and she is co-advised by Cyril and Sean, looking at characterizing shallow subsurface stratigraphy over the Schrodinger Basin on the moon. I'm glad I pronounced that right. She completed her bachelor's at University of Virginia as a double major in environmental science and statistics and a minor in astronomy. And she's also a part of the House of Gryffindor. She's an amazing first year here at UTIG, and I'm excited to see some of the work that she did in her undergraduate background and research. So with that, let's welcome Medha.
Hey, everybody. Ooh, a point. How fancy. Thank you for being here. So I decided that before I get into like my research, I'll like take some time to kind of like explain like my research path and how I got here, because I think it's kind of convoluted. So this over here is a picture of an outlet glacier that I had the fortune of hiking when I was in Iceland during my first year of college. And arguably this moment, it was just so beautiful. Everything looked so majestic. This was kind of like the moment that planted the seed in my head that like, hey, you kind of need to pursue the geosciences. And so that kind of like set me on a journey, which was shaped and influenced by wonderful mentors and lab groups that I wanted to take time to kind of talk to you guys about today. So I include this here because this was my like first little book and like geosciences that I had when I was an elementary school kid. I like made my parents buy that for me. And there's this one place that I saw in that book called the Giant's Causeway, which is in Northern Ireland. These really cool basalt columns. And actually the fortune of visiting it a couple of years ago. And I thought it was a really cool example of this idea of like the influence geology has on cultures and how cultures influence how we use our geology. So there's a really cool Celtic story behind this site, which basically says there was this Irish giant, there was a Scottish giant, they were fighting, and the Scottish giant got really scared and ran away from Ireland and left this in his wake. And so I think this is just a great example of kind of like this co-evolution. And it's something that really attracted me to studying this field as well as the actual science of it. And kind of throughout my time at the University of Virginia doing these degrees, I took a lot of coursework related to that. So I've done like archaeoastronomy, ecological anthropology, I've taken classes on the history of space exploration, all kind of pursuing that interest. I also had the fortune of being a part of these two wonderful lab groups, the Ice and Ocean group, and Dr. Lawrence Simpkins is the PI of that, and the Landscape Evolution group, and Dr. Adil Lemay is the PI of that group. And with them, I had a couple different projects. One was broadly understanding the deglaciating Northern Hemisphere through class analysis of outcrops from the Cordilleran ice sheet. And then also kind of using a mass morphometric analysis of a bunch of features of the deglaciated Northern Hemisphere to understand controls on certain meltwater feature formation, but then also understand that sort of drainage and its potential on Mars. During that time, I also was a part of the Origins and Habitability Lab at JPL, and with them, I wrote a couple of papers on carbon reduction in planetary and prebiotic environments, and also on the hypothesized metabolisms of Europa and Enceladus. So this is kind of like hopping all over the place, but I broadly knew I was interested in planetary science, and also kind of combining that knowledge of planetary science with our perceptions of the intrinsic value of these environments that we studied through astrobioethics. And all of these interests led me to you guys over here at UT, and I'm incredibly excited to be a part of this program and continue my journey over here. And right now I'm currently studying the shallow subsurface stratigraphy of Schrodinger Basin, as Michaela kindly mentioned before. And I have no clue what the rest of the projects are going to be, but that's what the rest of the few years is to figure out. And hopefully then I'll figure out what I'm going to do in the future. But today I'm going to be talking to you a little bit more about the work that I did during my undergraduate, specifically looking at subglacial water drainage on Mars using terrestrial esker analogs. And as a broader note, I am currently writing up a manuscript on this, and it is supposed to be relatively short. So any feedback that you guys have on aspects that you find interesting and compelling about the work would be greatly appreciated at any time convenient to you guys. Let me shrink this over here. So I mentioned these funky little things called eskers. So broadly, first, I can talk a little bit about the importance of glacial activity. It is a pretty significant contributor to water flow on Earth's surface, and as you'll see on other planetary surfaces as well. And one way we kind of understand that water flow is using something we call meltwater landforms. So basically any sort of landform, either erosional or depositional, that is created by subglacial meltwater. And eskers are an example of depositional features. So they're deposited by the glacial meltwater in a bunch of subglacial channels or channels that run through or over the glacier. That can be tens to hundreds of kilometers long, so super massive features, and on the magnitude of hundreds of meters wide and tens of meters high on Earth. And this is a lovely example of one in Canada, and I really want to see one. I've not seen one in my life yet. So, why is this not going? Okay. And what these features can tell us about an ice sheet is, one, that there was water flowing. There was an abundance of meltwater and sediment. Otherwise, warm-based glaciation. The alternative would be cold-based glaciation, where the ice sheet is frozen to the ice bed interface. Additionally, it can tell us a lot about the configuration of subglacial water drainage and the networks, just generally what was the arrangement of these subglacial water channels at time of retreat. And then also could tell us a lot about hydraulic gradients, so maybe direction of flow, orientation of the terminus of the glacier, etc. And very importantly, on Earth, these glacial features are very important for ecosystems harboring vegetation and being habitats for various organisms. They hold significance to many indigenous peoples, and they're actually a significant source of water for many communities. And so there is a lot of discussion about esker aquifer conservation and everything. So these are super cool features. And so you can imagine it would be pretty funky if we find these on a planet that we believe to be relatively cold, dry, desolate, like Mars. So this is an elevation map of Mars. These black dots over here are where mid-latitude, viscous flow features have been identified on Mars. Basically, we can't really call them, here's a Martian glacier, so we call them all these other names to be like, this looks like ice, and this might be very dirty ice, and it exists in this area. So there's a whole bunch in the mid-latitudes, as we're recently discovering, and the places where there are circles are previous study sites of potential eskers on Mars. In the mid-latitude regions, they're usually kind of pretty sparse. They might be like single eskers, but near the South Pole, they're like these huge systems of eskers, like thousands of kilometers long, rich systems. So it is very cool to be able to study these over here. And just showing what an esker would kind of look like on Mars. And so this is one from Tempera, one of the mid-latitude regions that I mentioned earlier, and some kind of key features that kind of define a Martian candidate esker are, one, that it's a long, sinuous, positive relief ridge. Typically they are transverse to the glacial margin. Sometimes it can be really funky configurations in which they are not, but that is not necessarily covered by my work. And then also sometimes if you have high enough resolution imagery, you can see that there are textured deposits over here. Another way you could kind of identify this, so this is one near the South Polar Layer deposit. Again, that same long, sinuous, positive relief ridge, sorry for the horrendous tracing. But then also you notice that it courses up and down topography. So in a normal sort of fluvial feature, you would kind of expect that water flows downwards, but water in a pressurized environment can actually flow upwards. And so you see that these depositional ridges actually course up topography, which are super cool. But they're not there's not always ways to verify that. It makes sense. You don't have a gigantic impact crater everywhere where an esker is. And so with all these interesting features, there needs to be a way to sort of not just qualitatively observe them and kind of discern what they mean. And that's where I think quantitative analysis can be super powerful. So this is not related to geosciences at all. This is actually from population genetics, a figure that I think is really cool that kind of represents how amazing quantitative analysis can be. So this is principal component analysis. For those who don't know what that is, you have many factors that define like all these variables that you're studying, and you smush it to 2 dimensions, and you're like, okay, now I'm going to visualize it. And so essentially, when looking at the genomes of fruit flies that are derived from all those countries in Europe, through quantitative analyses, they were literally able to like remap the geography of Europe from these genes. And I think that's super cool. And so I think there's no reason why it can't be applied to quantitate for geomorphology. And so that is why I decided to use that in my project. So with quantitative analyses, I hope to answer a few questions. One is, how can length, sinuosity, and crest elevation, these 3 different metrics that will kind of be the most important part of my project, describe eskers we see on Earth? And can these metrics be used to distinguish between fluvial and glacial features? Oftentimes when we see a positive relief ridge, there are kind of debates about the formative processes on other planets. And the most common, I guess, counter hypothesis to glacial features on Mars are that they're inverted fluvial channels. And then finally, what can these metrics tell us about the formative processes of the ridges that exist all around the southern polar layer deposit on Mars? And so as a basic workflow, I'm using a whole bunch of different data sets, either publicly available or from previous research, that have eskers across the deglaciated northern hemisphere, elevation data with DEMs that with resolution adequate enough to resolve those features. And I calculate those 3 metrics I mentioned earlier. So length is pretty intuitive. It's the length of the overall ridge segment. Sinuosity is basically a metric of how much an esker deviates from a straight line path. So the more kind of curvy or meandering that ridge is, the higher the sinuosity. And a sinuosity of 1 means that's a completely straight line. And then esker relief is the maximum crest elevations minus the minimum crest elevation across the esker, which basically captures the variability in elevation across this feature. And so a lot of the features that I am studying in the northern hemisphere were formed during the last glacial maximum. Eskers typically reflect conditions during the most recent glaciation. Usually there's like another advance of an ice sheet. Those eskers are like destroyed and not preserved. And so a lot of them will be from Canada, over 20,000 of them that were mapped by Storer et al. In 2013. And then also through the Brit Ice Initiative, they mapped a whole bunch of eskers in the UK, which have 2,000-ish eskers there. And then in terms of Martian ridge sites, I mentioned earlier that there were a few that have candidate eskers. Arjar Planitia is like the 2nd largest impact basin on Mars. And so that was one site of interest. And then also, a bunch of ridges around the southern polar layer deposit, thousands of ridges around the southern polar layer deposit, big pain in the butt to back. And so basically previous research had posed that these ridges were eskers, but had not really done terrestrial analog studies except for that one red site, Dorsa Argentea, to sort of confirm that. And so that is what I was seeking to do with my work. And interestingly, these ridges also have a hypothesis for when they were formed. So there were 2 phases of glaciation, one being this sort of late Milwaukeean formation over here through crater counting. This is how they dated it. And then also an early Hesperian, so slightly later, those ridges were formed as well. So that 2-phase glaciation is something that I want you to keep in mind for later. And so these are a lot of data sets and a lot of places. And so this is an outline of kind of how I'm going to cover them. First, I'm going to cover like terrestrial trends compared to Mars, do some Mars stuff, and then talk about why some analyses may not have been as robust and what I did to make them more robust. Okay, so basically, I plotted a bunch of these values for all these measured values for eskers. And as you can see in the 3D plot on the left, there's a negative correlation between sinuosity and length. And we interpreted it to suggest that persistent and efficient transportation of meltwater is indicated in longer eskers, and that would sort of make sense that your path would become more straight as your meltwater drainage would become more efficient. Additionally, we see that lower relief, so lower variability in this crest elevation, occurs for less sinuous and longer eskers, indicating that relief is minimized with both persistence. I can imagine that a conduit would become more homogeneous as water flows through the conduit, thus showing less variability in the crest elevation. And these are all from the terrestrial eskers, as I said before. When you look at the relations of these metrics across spatial distributions, so this is a density map of eskers across across Canada, and so you can see that those dark regions show really dense esker quantities, and then those lighter colors are where they're less dense. Previous research has shown that those dense eskers happen on crystalline bedrock, the Canadian Shield, as opposed to the more sparse eskers happening on more sedimentary rock. And so that could be one big reason for the density that we're seeing over here. But when you look at these metrics, in terms of that density, so first with length, we see that it actually decreases with esker density, which we interpreted to be ephemeral pathways of meltwater flow. Additionally, we see that straighter eskers correspond to denser areas, indicating that when more eskers are occupying the unit of space, there needs to be more channelized, efficient drainage organization in order to accommodate that. And then also we see that lower mean reliefs exist in these denser areas of eskers, in some indicating more temporally extensive glacial influence, because we also saw that those density of eskers increase towards the centers of the glaciation. Like when the ice retreats, that's kind of where it last remained, wherever those dense eskers were. And overall, you can see that the variability in these metrics decrease with the density as well. When we look at these metrics in relation to glaciations as well, so basically those dark areas represent glaciations where more glaciations have occurred in like the time before the last glacial maximum, whereas the lighter colors represent where there have been low glaciations. We can see slight differences in distributions of these metrics between these areas. So starting out with lengths, we see that the longer length eskers occur in regions with more glaciations. And then also the distribution becomes increasingly positively skewed, so more skewed towards the shorter length eskers as well. Additionally, we see that the sinuosity distribution becomes increasingly positively skewed with more glaciation cycles that have occurred in the terrain. And relief, we don't see any really significant difference between these distributions, which we interpreted to mean that it like esker relief or that variability in crest elevation likely represents glacial conditions at the time of glaciation rather than the broader trends in landscape evolution that length and sinuosity might represent. And so basically to summarize all of that, hopefully this is a very succinct summary. We see that the eskers with longer lengths correspond to those with lower reliefs and sinuosities, as I mentioned before, which means that a long esker relief, a metric that really has not been used before to describe these ridges, can be used as a proxy for flow persistence and duration of meltwater flow. Additionally, we see that the variability in these three metrics decreases with increasing esker density, which could be attributed to a bunch of different factors, but we thought that maybe bed substrate might be a good explanation, where softer sediments are less it's possible to form eskers on softer sediments, but they're just less conducive to esker formation, but also promote less uniform subglacial channel configurations like you would see in those really dense areas where there was that hard crystalline bedrock. Additionally, we see that the eskers formed in areas experiencing those higher amounts of glaciations have longer and less sinuous eskers, while there are no significant changes in relief. And we know that eskers reflect conditions in the most recent glacial cycle. Thus, these differences probably represent interactions with repeatedly glaciated terrains rather than the actual glaciation itself. And so now applying what we kind of know about these metrics to the ridges that we see around the southern polar layer deposit on Mars. This is a box plot showing the distributions of esker length for different populations in the Martian ridges, as well as the blue showing the terrestrial ridges. And you can see that these Martian ridges are gigantic. They're huge. They're so long. They're like tens of thousands of meters long. And they also have a greater variation in esker lengths than those on Earth as well, which is super interesting. Additionally, we see that both the sinuosities are very close to 1, and that is a pretty significant thing in terms of differentiating fluvial features and glacial features, because the cutoff sinuosity for subaerial river migration is about 1.5, and the distribution of sinuosities for a whole population of subaerial rivers essentially kind of peak at 1.5, whereas eskers are believed to be more straight, so closer to 1, and we're seeing that over here with our data. Additionally, we see that Martian ridges exhibit a similar range of crest reliefs to those of terrestrial eskers, but around 57%, so more than half of the terrestrial eskers would be considered low relief, and 20% of these Martian ridges are low relief, so much less of them, but that could also be attributed to the increased variability that would come with increased size of Martian ridges. And when you kind of plot these metrics against each other for both of these, you can see that the Martian ridges sort of conform to these to the trends that we see with the terrestrial eskers as well. I also did like a Welch t-test, like a statistical test, but I figured nobody wants to see p-values and stuff on the slides.
I do. Serious.
And we saw that like the sinuosity distributions were not said to be significantly different, but the lengths and reliefs were, which are super interesting. But you can see that they almost look like a subpopulation of terrestrial eskers that correspond to longer lengths, lower sinuosities, more persistent meltwater flow.
Can I
Yes.
interrupt you for a second?
Yeah.
This is where you do need to have some kind of measure of correlation. So, you know, putting up plots like this is nice, and I see that they're probably different or kind of, but there are metrics you can use on those statistical populations to say whether or not they're the same or different. I would encourage you to find out what those are and
For sure.
use them.
For sure. No, that's what I'm planning on doing for the paper.
Great.
Yeah, awesome. Thank you. I will keep that in mind. Yes, okay. Yeah, so it was a Welch t-test, which was a non-parametric statistical test, which basically compares the distributions of certain metrics between two populations. And so through that, we were able to see that the Martian ridges do conform to trends seen in the terrestrial eskers, and more closely correspond to the eskers that we believe to have more persistent meltwater flow than those that do not. So closer to maybe those Canadian eskers versus ones that were formed over softer sediments. Okay, awesome. And then a couple of notable sort of case studies that I saw when I was kind of investigating these features around the southern polar layer deposit. So this is in Parva Planum over there in the green box. And we saw these features that kind of resembled esker beads like that we would see on Earth. And these are viewed to form over a long period of time, over multiple melt seasons. And they kind of represent this variation in ice marginal drainage and sediment supply. Additionally, we saw things like esker enlargements, which were seen in Dorsa Argentea, which was that red ridge population that I saw on the top left. They're thought to represent subglacial conduit collapse, and their abundance is typically associated with faster ice retreat. And so, as John mentioned earlier, there needs to be some more robust things added into this workflow. And I think one of them that I'm going to add in is a few more statistical tests, which I'll get to later, but unfortunately we're not done in time for this presentation. But basically I mentioned a couple metrics earlier, ones of sinuosity and relief. So there were a couple things that I wish I had the foresight to do in my undergrad work that I now do have. And so the first one is that sinuosity have you guys ever heard of like the paradox of measuring the length of a coastline? Yeah, right, and so it basically depends on the scale at which you do it at, because you could get all those like little like curves, or you can be, or it could be much more broad. And so sinuosity is one of those measurements that needs to be taken into account for. And so a lot of the analyses that have been done on these ridges before, as well as by myself initially, did not account for that. And so the first thing I did was to interpolate these ridges. So basically resample the points at which I traced the ridges in a uniform manner. So I had a uniform ground to compare all these ridges on. So that was the first thing. The other thing is relief. I think a much more robust metric could have been used to measure that variation in crest elevation. So what I did is at those points I reinterpolated or resampled my ridge at, I sampled the elevations from all those points and took the standard deviation of those elevations instead. So it could account for any outliers or any mistraces that either myself or previous researchers have done in mapping these features. And I also added a couple of new terrestrial esker sites. So, okay, good, awesome. Additionally, I added populations of eskers from Finland, and then also from Poland. And Poland, the Polish eskers are really interesting because they're formed over softer sediments, and they're formed in N channels instead of R channels, which R channels are basically channels incised upwards into the ice space, and then N channels are incised into the sediment. And so adding that as like a new population would also make my interpretations of sinuosity, length, and relief a little bit more robust, and still some tests need to be done in comparing those with other terrestrial esker populations. But I can show you some preliminary results from those. And so these are also plots for my new metrics. You can see that for the Z standard deviation, they more or less kind of look like the same trend that we're seeing for the esker relief, like the maximum minus the minimum. But I feel much more confident in these results than probably the first one. Additionally, you can see on the left, the orange dots being the Polish eskers, and the blue dots being the eskers from the UK with the length and sinuosities. And I see this and I think that there will be some interesting things to test between these two populations, either using a KL divergence test, as I learned from Alice, to test the differences of these populations. Additionally, this is what this new sort of metric for variation in elevation of crest relief looked like for the Martian ridges. And you can see that all of these different colors represent different sites around the Martian polar layer deposit. And you can see that some of them do look different than others. And so that led me to want to investigate these differences a little bit more. And so Martian fluvial, when analyzing these Martian glacial features before in previous work, I had not seen a single comparison to Martian fluvial ridges. And I think that's pretty important, because learning if these metrics are even able to differentiate between Martian fluvial populations and Martian glacial populations are important for analyses rather than just comparing them to terrestrial analogs. And so this is from Aeolus Dorsa, a mid-latitude region, which has a bunch of inverted fluvial channels, and extensive research has been done on this region. And so when I actually plot the sinuosities and the lengths of the Dorsa Argentea, so that area around the southern polar layer deposit, which through multiple morphometric studies have been confirmed to be, or very highly likely believed to be, eskers, compared to the inverted fluvial channels, we see that generally higher sinuosities can exist for similar length eskers in the fluvial channels versus the glacial channels, and that is something that I also seek to test statistically. This is very recent data, and so I hope to use the tests I mentioned before to sort of test if these distributions are different, and then how similar those new ridges that I've been analyzing are to these two distributions. Additionally, when we looked at the length and standard deviation for these glacial versus fluvial ridges, we can see that there are there's, at least visually, there seem to be differences, and it's yet to be tested statistically. But I'm really excited to learn more about why am I seeing distributions like this as well. And then additionally, going back to these ridges around the southern polar layer deposit, now in comparison to these two populations we're seeing here, remember how I said that the right side of that image corresponded to an earlier glaciation and the left side corresponded to formation several 100 million years later. And so we see over here with these ridges that most of them have sinuosities that are like basically at 1 or really close to 1. And then for these ridges over here, we see a different story where there are a lot more ridges that have those higher sinuosities for the lengths. Additionally, this really one funky population over here that I don't quite understand yet is also kind of like they attain much higher sinuosity values and are now all extremely short compared to any of the continuous sinuous ridges we've seen elsewhere as well. And so this makes me wonder about if this is reflecting a difference in the nature of the ice sheet's retreat during those two time periods in terms of what caused it. Subglacial volcanism is believed to be the main mechanism through which meltwater was sort of like disposed of in the later glaciation, so the ones on the left, and that might be reflected in the higher sinuosities and the more variability in configurations we're seeing. Whereas maybe the glaciation on the right had a much more sluggish and stable retreat in which we're seeing these very low sinuosities as well. When you look at the reliefs or the variation in crest elevation for these regions, you can see that also there are similar distributions for the ones on the right and ones on the left again. So this dichotomy of different morphologies, which I was not really expecting to find. And then the outlier of that orange box site was also kind of weird, and I'm still yet to understand that. I don't think that they're eskers, but I think that they might have been formed through glacial processes because you don't really see that same sort of potential for longer lengths that we see with the other eskers as well. And so from all of these crazy data analyses with more to be done, I would say that there are a few preliminary conclusions. One is that we see that the terrestrial eskers show correlations between length, sinuosity, and relief that allude to long esker relief as a proxy for esker maturity. Additionally, we see that, oh, that's the other one, my bad. We see that the plant forms, so that two-dimensional geology, the length and sinuosity may reflect interactions with repeatedly glaciated terrain, whereas the esker relief may reflect conditions during the most recent formation of them or the most recent glaciation. For these eskers to form on Mars, typically like what controls esker formation is an abundance of superglacial meltwater and an abundance of sediment. And so for these really long, large features to be formed on Mars, there had to be an abundance of superglacial meltwater and sediment for maybe multiple melt seasons, hundreds of melt seasons, especially for things like those esker beats to form or just for these really long bridges to form. However, these pathways of persistent meltwater drainage do not necessarily preclude intertwined networks of pathways formed synchronously, so over the course of maybe multiple days or weeks, or by sudden processes within the same system, as we see through the esker enlargements we saw in the ridges that were dorsal Argentea ridges, which were typically thought to have formed through very sluggish ice retreat. Additionally, we see that when we use these metrics to compare Martian fluvial ridges to Martian glacial ridges, that eskers have lower sinuosity than Martian fluvial ridges, as we see on Earth and as we expect on Earth. Additionally, we see that differences in retreat style between the late Noachian, so those earlier ridges and those late ridges in the early Hesperian periods are reflected in the ridge morphology. Alternatively, I think that some of those ridges are not actually eskers like previous studies have hypothesized. In order for these eskers to be preserved, if ice retreated past these features on Mars, then they would likely not be preserved. And so maybe ice after those, like 3.8, 3.4 billion years ago, ice never really advanced past that, past those extents of those eskers on Mars. And that is interesting because there have been some recent hypotheses about the nature of volatile cycling on Mars and how it would be repeated advances of ice sheets and then redeposition at the pole. And I just don't think if these are still there, that was possible. And these are my acknowledgements. I had a wonderful lab group who helped mentor me through this. And then also a lot of people who have a lot of expertise on the subject. I've had some very helpful discussions with them. And it was funded by the VA Space Grant Consortium. I'm sorry if that was very convoluted, but hopefully it was interesting. Thank you. Alice.
Can you go back to one of your plots where you plot all of the things against density?
Yes. No. There we are. That one.
How much of what you see here is just reflecting like preservation of like the eskers? Like surely there's other processes that get rid of them, and how is that kind of like biasing what you see here?
That's a great question. So yeah, there's a lot of post-depositional modification that can happen to an esker on Earth. And I thought personally that it was actually reflected in that sort of relief metric that I was talking about earlier. So it's a variability in crest elevation along an esker. So I'd imagine that if you have a longer, like, where's a good example of this? Give me one moment. Yeah. Okay, yeah, this one. Do you kind of see how like there's this like bottom slope that's like upwards in the data over here? I think that is because that when you just have a longer ridge, there's, I don't know if opportunity is the right word for it, but there's just more availability of space and more availability and more opportunities for like variation along that ridge spatially. That could be, and more opportunities for that post-depositional modification that kind of had this minimum, like that's why you see like this increase in like minimum relief that you would expect for like a longer esker. I don't know if that makes sense. Like there's just more opportunity for variation in that post-depositional modification that would bias towards longer eskers, actually probably not the shorter ones that we see in the denser areas that you're seeing earlier.
Okay.
Yeah.
What's the surface age of this area, of like the Martian region?
The Martian region, so, where is this slide? Wait, did I put this here? I might put it, I think I put it, yeah. So this was done through crater counting, and so the area for these ones on the right were dated towards the late Noachian, in that age over there, like about 3.8 to 3.7 billion years ago. The ones on the left were dated to be about 3.4 to like 3.4 billion years old. And this region over here, I think they actually were not able to obtain dates for, because it was hard to like get the adequate like craters and the cross-cutting relations to like be like these are applicable craters that we can use for crater counting versus not.
In that case, since they're that old, you might want to look at the change in the tilt of Mars
Change.
over time. Because it's gone through quite a bit of like
Liquidy
liquid changes in the
Hmm.
last 100,000 years, which is definitely within the range of those surface ages.
Okay.
And so you might see that the expected location of the southern polar ice cap shifts by like 5 degrees, and it'd be interesting to see how well these eskers correlate with the paleopolar. Yeah.
Okay. I'm gonna write that down.
Yeah,
I
I
didn't-
think, doesn't Mars has like chaotic obliquity, I think? where
It
it's,
does.
like pretty.
Yeah.
It's not a nice,
Especially that weird orange region. I would be surprised if maybe that's like
of paleopoles, maybe that's why it just stands out as weird, because it's
Yeah.
just like that was a pole.
Yes.
Yeah.
Did Mars have true polar wander too? And that's what put the volcanoes at the equator?
I think that's what
Maybe
they
this is
say,
like
yeah.
A purported kind of thing.
I've like heard it, I'm not.
Yeah, I don't know what the
that
timing of
interested,
that
but
religious
Yeah,
piece as well, but
yeah,
I always think about paleoclimate.
Yeah.
True polar. I have a question. So
Yeah.
why do you think the Martian eskers are longer? Is it because of gravity? Is it because the rocks are different?
that's a good question. So I think, so lower Martian gravity would allow for lower stress values when the water's flowing and able to erode the sediment. So like there, I think we're not sure, but that could be one explanation that is just able to take more sediment with it because there's just a lower threshold for when for the stress values needed for that sediment to be eroded. Alternatively, the esker terminates like with like the closing of the subglacial conduit. And so lower gravity value can maybe mean that like it takes longer for that conduit to shut down. And thus we're able to generate such long eskers. Maybe in the regions on the left, there were a lot more like synchronous forces than we think that there originally were. That could also result in such continuity of them that we see. Like previous research has shown that the ridges of Dors Argentea like are way more continuous than the terrestrial eskers. And so that could also be an explanation for it, but we don't know. Yes.
How do you know the age of the eskers? Because surely this is just the age of the crust that the esters are eroding.
No, so they did specifically use like crater, like they did crater counting kind of on ones that seem to like overlie the eskers, and I think then they used like overall trends in crater counting corresponding to age for like the surface area that they were actually able to address when they were looking at the terrain specifically covered by eskers. Like I don't know if that makes sense. They use a smaller terrain, extrapolated it to like a larger trend in crater counting correspondence to age.
So the crater like cuts the,
Yeah,
okay,
there's some that are like actually on top, yeah.
and
yeah.
it doesn't like obliterate all of your data then?
No, it does not, luckily. Yes, Cyril?
Looking at the map here, do you think it's, I still see some eskers that are pretty close to the current cap.
Yeah,
Do you think it's reasonable to search for eskers that are still physically connected to the cap in order to search for ice caves or stuff like that?
I think so, especially in those Casmata over there. We even see right now, like in the, like, we thought that the Amazonian, so that's like the most recent time period of Mars. We believe it to be like a cold and dry climate, but we still, in those mid-latitude regions, that I sort of mentioned earlier, like over here, here, and here, those are like believed to have formed within the Amazonian period. So this very cold, dry period. And those only yielded like very like much smaller amounts of eskers than we see from this overall ice sheet over here. And those are also believed to have been preserved through sublimation. So the solid ice does not like melt into water. It just basically directly turns into gas into the atmosphere. And so those are, and like the example that I showed earlier, also shows like an esker still directly connected to its parent ice body. So I think it is plausible for the South Pole for sure. Yeah. Carrie?
Question. Are there eskers at the North Pole? Is that the smaller North Polar residual cap? Or the South Polar residual cap?
I haven't checked, but
Okay.
I haven't seen anything related to that really.
Why not?
What is bad imagery of the North Pole?
Yeah,
I remember.
I think so.
There's good imagery everywhere on Mars.
We know you're salty about it.
Is it possible in some of those like locations you have a mix of both fluvial and glacial ridges, so it's not just either or.
Yeah, I think so. There could be like pro-glacial features as well. I think like for such a like wide spanning area over here, I think there's no reason that the ones that are like away from the ice cap can be like fluvial in origin and ones closer are not. I think there was this time where I was like, oh, maybe I'll look at like the difference in elevations of like the bifurcations of these ridges. So like basically where the ridge branches down to two for inverted fluvial features. We would expect that there would be one to be significantly lower elevation and one to maintain the same elevation as kind of like the original ridge. Whereas eskers, you would not see that stark difference. And I think some of the ridges over here did show that. So that is why I also think that not all of them are glacial on that left side, as previously thought.
How were they mapped? Just out of
Mapped.
curiosity, because this resampling thing, like if you plotted them, like you would calculate a stream on Earth.
Yeah,
It's just a function of the resolution, the DEM, so the sinuosity should be uniform.
yeah,
Or like that, what you were saying, like the, it's gonna be like the English coastline that like is removed just by the resolution of DEM.
yeah, for sure. So I use this software called JMars, which is this open source software where it aggregates like a bunch of remote sensing data of Mars. And there was like DEMs where you can actually take like profiles to like double check that is indeed positive relief, but then also it has really high resolution like CTX imagery, which is like 6 meter resolution. So you basically previous research kind of demarcated these regions of interest, like of candidate eskers. I just went in again with that really high resolution imagery and we're able to like trace the points. And then resampled was just to ensure that the spacing between the points I picked were uniform. Yeah. Cyril?
So the South Polar Cap that extends further down on that map.
Yes.
Usually, and do you see, so there's kind of big, what we call a lingula, right?
Yeah.
And so do we observe eskers around that other part of the South Polar Cap?
I haven't checked honestly, and previous research also has not like examined that area, but I'd be happy to look. Yeah. I think it was interesting when, oh gosh, who was visiting? Oh, Nana Carlson, that's who was visiting. Yeah, she was saying that like, isn't that bright spot in radar kind of like identified like towards the south? I found it kind of ironic that I didn't see any, any ridges around that area, so.
It was almost right on your person.
Yeah,
But I was asking for the esker question down to this area actually, because I don't remember to have seen any reports about eskers there.
yeah.
And so if this is correct, there is no esker there, what does that mean for that region of the cap?
That there is an abundance of meltwater over there, and so even under Mars' current regime, with the pressure that's provided with like with the ice sheet or like those glacier-like forms that are in the mid latitudes, that pressure can be high enough that like the temperatures that exist on Mars are conducive to some subglacial meltwater. And so it's possible that it is just like pooled over there and some sort of mechanism was able to let it out either through like some subglacial volcano, an impact or something like that, that was able to let it out and form the esker. Yeah, and if there are multiple eskers, then that's something that we need to look into.
Is it also possible that that lingula, the spatial extent of that lingula more or less matches what the maximal extent of the SPL that the SPLE had back in the time?
It's possible. I don't know, because like these represent to me that the maximum extent of that ice sheet just never passed that point after these eskers were formed. But especially if there are other meltwater features that also preserve like the last glacial extent that are identified over there, that also could mean that and are like dated to similar times, that could also mean that the ice sheet would not like, that was, this was like the maximum extent of the ice sheet, but again, we don't know. I think there was also some hypothesis somewhere where it was like, there was full ice coverage on Mars or something like that, but, yeah.
Compare Mars and Pluto.
No.
Any final questions?
There's someone on the, oh, that was just a comment.
The,
That was just Sage.
Said, great job.
oh,
Let's
say
great
job.
Let's thank Meta one more time.